All right. Good afternoon, everyone. It's a Thursday afternoon in July. I've got a really cool guy with us today. Trevor, we're going to let folks get online here and then we'll get started and I'll do an introduction, but glad you could join us today.
Glad to be here.
So we'll give folks a few minutes to get their Zoom set up. I know some of these folks are, they put it in their conference rooms and a few of them sit around and eat their cheese sandwiches or drink their coffee in the afternoon. So we'll give them a minute. See some familiar faces coming in there too. So today's session is part of the Enbridge Critical Building Science. So this is a provincial series, and I think we're going to have some folks from even out of province, but it is definitely about building science. And about a topic that might be just a little contentious, maybe, you think, Trevor? Or...
There's definitely some contention sometimes.
Yeah. About something that we definitely have to have, which is a roof over our head. All right, I'm going to go ahead and get started because we want to give Trevor as much time as we can today. So welcome everyone to the Enbridge sponsored building science series called the Critical Canadian Home Building Science Part 4. And today we're going to be talking, I'm going to say Trevor, our expert, Trevor Trainor, Bawating Building Science, is going to be walking us through high performance attic and roof design best practices. We're glad to have Trevor with us today. Let me get my slide moving there. So just real quick, we're going to be going through, Trevor's going to give us some of his experience. Trevor's been involved in not just tearing things apart, but designing things and finding out whether it works or not. Is that fair to say?
Fair to say. Yeah,
good. He's going to give us some best practices. He's going to talk to us a little bit about code. And again, we're going to be talking about things like even attic rain. You know, it's interesting, isn't it? Like building codes over the last many years have been requiring more and more attic insulation, which is okay. We get it. But it is changing the dynamic of the house as a system. You know, air tightness and you know, tight assemblies, things like that. So Trevor's going to get us into this. So for today, for those of you that are online, a couple housekeeping rules. If you have questions for Trevor, which we want, put them in the Q&A. Don't put them in the chat. Over in the chat, you've got Stacy from our building knowledge team. Stacy Cooper's on there. And if you have technical issues or you want more information or you're looking for sources, hop on the chat and Stacy can help you there. She may be posting some links to some of Trevor's work or some of his recommendations. So keep an eye there. The other thing too is after we're done today, we really do need you folks to fill out the Survey Monkey. We love having you on. These webinars are good. A lot of the reason is because of who you are joining us with your questions, which makes these webinars good. But Enbridge and ourselves do want to get some good information back from you. It helps us build the sessions, helps us do them better, and also to maybe dive into some other topics. So that's why we need your survey. And as always, remember that immediately following the session today, you are going to receive an email that'll be coming out from Stacy and our team at the Building Knowledge Canada webinar. And you will receive a copy of the presentation. You're going to receive access to a recording. You're going to receive links. Lots of good stuff. So no need to ask for it, no need to request it. You're going to get it just because you're signed in. So before we get started, we do have a couple things for you. Real quick, Stacy, let's roll the first poll. Tell us, where in the world are you joining us from? So geographically, where are you today? Even if you're traveling, let's go with that. Don't tell us where you live or where, tell us actually where you're calling in from today. So take a minute and just fill in any of those areas. And if it's none of these, go ahead and put it in the chat. Yeah, we've had, you know, it's interesting about building science, isn't it? That it's all about climate, but it's not about borders, is it? All right, what do we got here? So we've got a lot of folks from Ontario. So Trevor, we've got close to 50 from Ontario. We've got some folks from BC, Alberta, Saskatchewan, Manitoba, Quebec, and the Atlantic provinces. That's a pretty good representation.
Nice.
Good deal. All right, folks, one more question for you. What keeps you busy day to day? Give us a background, who you are, and what you do, what keeps you busy during the day. And again, if it's not on the list, feel free to put it over in the chat. By the way, did I not see that there's someone from the Ukraine here? Look at that over in the chat.
Wow.
Vladislav, good to have you. Very good to have you. Armando, look at there. Designs zero energy homes he's from Texas, but works on zero energy homes in climate zone 5 and in the US. Good deal. There you go. Now we can talk climate zones. That's good. So who you folks are, we've got a good portion of builders and renovators, the folks that actually do the work, which is pretty cool. We've got some engineers, some sales reps, manufacturers, designers, got some energy advisor, HERS raters, registered energy advisors, and building officials. Excellent. Well, it's good to have you folks online. Trevor, that gives us a pretty good idea about who's on here today.
Great.
So real quick introduction to Trevor. Trevor is the president and a building science specialist at Bawating Building Science. He founded Bawating Building Science, works in the area of hydrothermal performance for enclosures and in extreme climates, cold climates. Trevor has a tremendous amount of background in hydrothermal performance of all types of assemblies, and has been involved in a lot of not just studies, like actually testing stuff in the field to see if it works, but like I said earlier, Trevor, you've tore apart a lot of things to see what happens, right?
A lot of forensic stuff for sure.
A lot of forensics. In fact, I was just saying to Trevor earlier, we need to have him on to do one on do some like a forensic case studies. You know, I've always joked that I'd love to see a builder, designer, renovator that would buy back a house or a building that they had built 10 to 15 years in the past and tear it apart piece by piece just to see how it worked. You know, that'd be sort of interesting. All right, Trevor. Well, listen, again, before we move on, I do just want to thank the Enbridge team. Susan Cudahy leads their residential sector. There's a number of other Enbridge folks that support this as well. Enbridge has been a great sponsor of these sessions and a tremendous supporter of the building industry and best practices. And it's wonderful that they can support things like this. So Trevor, I'm going to hop off and away you go.
All right. Let's see if I can share my screen today. If I show the right one, I think it's all right.
No problem. Looks like we've got some academics, some warranty providers as well online. So there you go. Now we know who we can talk about and who we can't, Trevor.
Yeah, for sure. Well, it'll be interesting. You mentioned forensics. I do touch on a couple of forensic examples in this presentation also. I find it's always very useful to understand when things go wrong, why they went wrong, and what can be done to fix them. So
very cool.
Yeah, you can see my screen there now, Andy. I'm good to go.
We can. Yeah.
Excellent. Okay. Actually, what I'm going to do, that'll work. There we go. So I call this presentation a new slant on roofs because I think there's been, quite a few changes in the last 10 to definitely 20 years on residential roof design. So we're going to touch a little bit on commercial just from a performance standpoint, but we're really going to talk about what's going on in the residential sector in terms of roof design and what kind of challenges that brings along. And again, we're going to talk a few examples, and we're going to do a little bit of building science along the way so we can understand some of the mechanisms that are causing the problems or, potentially helping us out also. Mm-hmm. So there was a time when there's basically two types of roofs. We had to see our typical residential roof. We see, hundreds of thousands of these. They're typically very simple roofs. They're sloped roofs and they're vented roofs. And the reason we see so many of these residentially is because they they work. We know how to build them. They have, the trades, the materials are all available, the knowledge is there, and they just generally work, with some exceptions that we'll talk about, especially when we get into more modern designs. Then on the other hand, we had this typical commercial roof. So we have, again, just hundreds of thousands of these, millions of square feet of these roofs that are very simple, they're flat, and they're unvented. And they work really well too. And the reason why, we see so many of them is because they work. They're pretty simple and relatively affordable. So, when we have these two different types, we know how to do them. It works pretty well. Where we start to see issues is when we sort of mix and match these things. So in the residential arena, what I'm seeing are a lot of flat roofs, a lot of these roofs that are, have high sloped along the side, flat on the top. So there's sort of a combination of the two. I guess even these aren't really a typical mansard that we would have seen in the 70s or 80s. These are different because there's a living space up in there often, and a lot of complexity to these types of roofs. So we see a mix of sloped sections and flat sections. And what we are seeing is when we attempt to ventilate some of these types of roofs, like we did with our classic residential roof, it's really difficult to do. We just get poor ventilation out of them because of the geometry, typically, and because of the construction techniques we use. So these are the ones we're going to really talk a bit more about in detail, and what type of approaches we can use to address some of these more complex roofs.
Trevor, it's funny, that picture you have of those flat roofs, that picture on the left is probably about 70% of the product we see coming across our desks here in the GTA. It's known to the home builders as what's called the missing middle. It's that affordable, not quite mid-rise, high-rise, but that wood-rise. And it is a real struggle to even find trades that know how to do that type of roof. So anyways, that's
yeah, and as you can see in this picture, so this was a development beside one I was working on. The development I was working on looked a lot like this, but they used an unvented roof approach. In this one, you can see that they're attempting to use a vented roof approach.
Wow.
About more about why I don't recommend that. So to get down to some of the building science fundamentals that are behind this, we're going to talk mostly about air movement in buildings. So for air leakage to occur in a building, we need two things. We need a pressure difference across the building enclosure or within a building enclosure, and we need some type of hole. We need some pathway for the air. So if you have pressure and no holes, if you have a perfect air barrier, you'll have no air leakage, right? You can have holes without pressure potentially, and you wouldn't get any air leakage. It's only when we have those two of them together, if we have a pressure difference and a pathway, that we're going to see air leakage into or out or both of a building. And so it's important to realize that there's two factors at play, and they play off each other, as we'll talk about in a little bit, in terms of a balancing act there. So the first thing we think about typically when we talk about pressures on buildings is the wind, right? The wind's the most extreme pressure that a building will see. And wind pressure is very much a function of the wind speed, so in the area that you're in. The building geometry, is a tall building, a short building, and also what's around it. What's the local topography? Is it sheltered? Is there a wind tunnel due to high-rise buildings tunneling area? And so this is a very complicated thing for an engineer to try and estimate because of all these factors. So obviously in these three examples, we're going to see very different wind patterns and peaks and averages that are going to be very different. And so it's difficult to predict, especially when we're designing a building. Obviously, this building on the cliff is custom designed. They knew exactly where it was going to go. If we look at the bottom right example, all of these houses, as they're designed, it's not really specified which direction they're facing or what's around them. So it's not something we can really design to, but it's an important factor. The other thing we need to remember about wind effects, the peaks are really what we're worried about in design, not so much from a building science standpoint, more from a structural standpoint. So the peak wind pressures we see can be 30 times greater than the next type of pressure we're going to talk about, which is stack effect. So the peaks are really high for wind pressure. And it is important to think about those peaks in terms of structural considerations. How is your cladding attached? Rain penetration, it's important to understand those peaks for that reason. But overall, the average pressure due to wind is actually a lot less. It's only 1/10 of what the stack effect pressure would be on a building on average, which we'll talk about next. So it's really that long-term average that's actually, it's not that important from a long-term averaging standpoint. It's not that important from an energy analysis standpoint or a natural ventilation. If we're trying to use it for natural ventilation, it's not very reliable. Because although the peaks are high, the averages are very low. And so definitely less effective in terms of relying on wind pressure to help us.
Interesting.
So, yeah. So we don't really want to rely upon wind pressure as a significant contributor to attic ventilation. Is really one of the points I wanted to make here.
That's an interesting point, because my background as a builder, and of course we do building science training, is it's very easy to think, well, the wind's always going to depressurize, it's always going to carry the bad stuff away. Your point, it's not reliable. It's
not reliable. It's could be creating a positive pressure one day and a negative pressure the next day, depending on directions and depending on what the surroundings of the building are. Okay. Yeah. So wind affects the one we think about the most, but it's probably not the most important in terms of roof ventilation, which is sort of what we're going to talk a bit more about, and or even air leakage potentially. We might realize that stack effect is actually probably more important. So stack effect pressure is a function of the temperature difference, right, from inside the building to outside, and of the building height. And so it's probably important to note here that this is really a cold climate focused presentation, and we're assuming that a lot of our we're in the heating season for a large portion of our year. Because if I was to try and give this presentation in Texas or in Arizona, we'd be talking about a lot different things in different ways, because stack effect's not nearly as important there. So, but as a cold climate focused group that we are, for the most part, stack effect is really important in terms for two reasons. The first is the effect it has on air leakage in our buildings. So stack effect pressure is a result of the different densities of air at different temperatures. So we can just see here as an example. If we have 20 degrees Celsius air inside, it has a density of 1.2 kilograms per meter cubed. Whereas if it's -10 outside, the air density is 1.34 kilograms. So this air inside the building is much lighter than the outside, and it wants to rise up. So just like a hot air balloon is going to want to lift that air balloon up, this is going to try and force air out the top of the building. And if air can leave the top of the building, it's going to try and suck air in at the bottom of the building. So we have these different pressures at different areas of the building, and where they kind of meet, where we go from a positive pressure to a negative pressure. In this zone here is what we call our neutral pressure plane. I won't talk a lot about it, but it can be useful to determine where the neutral pressure plane is in a building. Can be useful forensically to find out where the holes are. If there's more holes high in the building, you'll have a higher neutral pressure plane. And if they're lower in the building, you'll have a lower neutral pressure plane.
That is cool.
So that's something we can quickly measure in a building and determine where that neutral pressure plane is. And we can use that information to help us. But really the key point here is that this stack effect, whenever it's cold outside, we're going to have this, and it's warmer inside. And the colder it is and the taller your building is, the higher these forces are going to be on your building. And it doesn't change day to day, changes season to season, but not on a daily basis due to like wind does. So what can we see? We can see pressures in the range of about probably 6 pascals of pressure, positive at a roof and -6 in a basement, say for a 3-story townhouse, for example. It's pretty typical. Again, depending on the height of the building, depending on the temperatures outside. But remember, this is sort of a constant pressure from a day-to-day perspective. So if you do have leaks up high in your building, you're going to get that air leakage outward, and it's going to be pretty constant. It's not going to be just during the day or just at night or just when it's windy. It's going to be pretty constant. And so the cumulative effects of that, of air leakage, is actually makes this stack effect really important, as opposed to wind effects, which may create air leakage at a higher rate, but only for a couple seconds at a time. So vented roofs, that's important to, I think, understand when we talk about getting to venting roofs also. So not only does the stack effect pressure affect the building, it actually affects our vented attics also. And so I'll get into that a little bit more. So vented roofs we're going to talk about first, and why they usually work and why sometimes they don't work. So if we had this, I kind of use this sort of simple diagram to help understand some of these effects. And we use this also in some of our forensic cases to kind of explain what's going on. So if we had a perfect air barrier in our building, we're still going to have this 6 pascals of pressure trying to push air out of the building. But if we have a perfect air barrier, we're not going to get any airflow. We'll get some heat loss from the building into the attic. And so what that's going to create is the attic's going to be a little bit warmer than the outside temperature, just from that heat loss, but only a little bit. And we have no moisture that's able to move from inside the building into the attic if we have that perfect air barrier. And so if we have a perfect air barrier, we don't really even need ventilation, right? And this is going to kind of come back when we talk about unvented roofs and how they can work. But the reality of the situation, especially in our typical roofs, is that we've got these holes, right? When we're typically using polyethylene sheet as our air barrier, it's really difficult to make that very airtight. We've got lots of penetrations, we've got joints, and we've got transitions in areas that are difficult to seal. So in reality, we're probably looking at this, where we're getting a certain amount of air leakage from inside the building. And because of this stack effect pressure, it's going to constantly go into the attic. And if we have no ventilation in our attic at all, it's just going to build up. You're going to get a warmer temperature in here. We're going to have very high humidity till it basically hits 100% humidity. And that's when we start to see our attic rain. Or in this case, depending if it was really cold out, it might be attic frost. Right. That will turn to attic rain on the first warm day after that. So that's one of the things forensically we always look for. If someone says they had moisture coming down into their drywall, was it the first warm day after a long cold spell? That tells us a lot. Versus was it after a big rainstorm? Obviously, that's a totally different clue. So this is probably more typically what we're going to see in terms of we know there's going to be air leakage, and now what can we do to deal with it? So the way we deal with it, and it seems to work really well for us, is to ventilate our attics, have openings low down in the attic and openings high up in the attic. So we talked about the stack effect that's happening in the building, but there's also a stack effect occurring in the attic. Because it's a bit warmer inside the attic than it is outside, we have that same effect. It's going to be much smaller, maybe like a 0.5 pascal or something like that, but it is a constant pressure that can create airflow pathways that we can use to ventilate our attic. So we still have this air leaking in, but now we have a way for it to get out, and we have a pathway for it to get out. And so the air paths would probably look something like this, right? We've got our warm, moist air coming into the attic, but we have cold air, cold, dry air coming through and flushing it out. And really, it's this that is the reason why these typically work. And they typically work really well in our climate and in other climates also. So that's sort of the dynamic we're looking for. And it really, I think the next slide shows us that it's really it's a balance though, right? If we have too much air leakage and not enough ventilation, we're still going to have problems. So it's really it's the balance that we're going to see between how airtight our ceiling plane is and how well ventilated our attic is. Another important thing to think about here is, so this is a sloped roof, right? And there's a certain height difference here. And we're really relying on the difference between our air intakes and our exhausts to give us that stack effect.
Yeah.
And so the steeper the roof, the more stack effect we'll have in our attic, the better ventilation we'll have. Which kind of brings us to our next example is we have this flat roof. We still have that same air leakage like we did before. Let's just say we just put poly vapor barrier, bad insulation or blown in insulation. We still have that same air leakage issue we had before. And we have an airspace here and we have openings, but what's the driving force to take that air and flush it through?
Wind.
Wind is all we've got.
Exactly. That's right.
And is it
not
blowing?
very often.
Is it blowing today or not?
Yeah.
Is it being blocked by a high rise beside us? There's so many factors, right? Because we don't have that height difference anymore to create the stack effect to get reliable ventilation.
Yeah. It was interesting, Trevor, on your last slide. I know some of the folks on the line to be aware with this. There are some provinces in Canada that have required soffits be blocked or sealed soffits, non-venting soffits, because of zero lot line clearance between homes. And it's part of the fire code. Well, in doing that, what happens if you have a roof vent and a soffit vent? What if you get rid of the soffit vent? Does that pretty well short circuit that?
Yeah, you'll dramatically reduce the amount of ventilation because that air that's leaving has to be replaced by something. So if basically you've kind of maximized your ventilation at the top to whatever your air leakage rate is.
Oh, wow. Okay.
And as we actually need quite a bit more, probably about 10 times more ventilation than we have air leakage in order to really flush the system out and keep moisture from accumulating in the attic. So that could be a problem for sure. And so, yeah, so this is why I don't recommend attempting to ventilate a low slope roof like this, because we don't have that reliable stack effect due to the height difference to drive that ventilation regularly. And we're really just counting on wind. And I think it was John Straub who said that's the Dirty Harry approach to ventilation. Are you feeling lucky?
Yeah, that's right.
Right.
You feeling lucky, kid?
So I never feel lucky. So I like to have reliable sources of ventilation. So again, this balancing act, right? If we're going to keep moisture from accumulating in our attics, it's really, we need to make sure that we have sufficient ventilation and low enough air leakage from the building so that balance is maintained.
Hey, Trevor, real quick, and you might talk about it in the future, but we did have one comment, use a roof ventilator, use these fan powered assist, or remember the old squirrel cages we put on the roof and the wind would blow them and it would suck that bad air. Right. What's your thought on that?
Right. Yeah, I don't address that directly, sort of indirectly, but yeah, the interesting thing is if right now, in this example, we have a 0.5 Pascal positive pressure in our attic, and that means the air wants to flow out. If we start pulling air out, we might create a negative pressure in here relative to the building. So let's say we had a power vent as a big example, or 2 power vents, and they're sucking air out. Well, the problem is now we're creating a negative pressure in the attic relative to the building, and we're going to start exaggerating this air leakage. We're going to make it worse. So it doesn't help our balance. We're increasing one, but we're also increasing the other. So we kind of end up in the same place.
I remember someone, there was a project, CMAC project a number of years ago in Sudbury, and they had attic rain. So they put in the squirrel cages. And what ended up happening is it exaggerated the leakage. It pulled more moist air in. And about a month later, someone was saying you would see plastic bags over top of these squirrel cages.
I have seen that.
Interesting.
Yeah, so the last little bit regarding vented roofs is what does the code say about this, and how do we sort of think about it, and how do we interpret it? So section 919 states that where insulation is installed between the ceiling and the underside of roof sheathing, a space shall be provided, and vents shall be installed to permit the transfer of moisture. Except I skipped one part. At the very start of this, it says, except where it can be shown to be unnecessary. It's a pretty big clause and really interesting, I think. and require some interpretation. And they do give us a note here that we can refer to, A91911. So what does that say? Maybe that'll clarify it for us. So A19.1, let's see, I'll just read it straight up. Controlling the airflow of moisture by air leakage and vapor diffusion into the attic or roof space is necessary to limit moisture-induced deterioration. Makes sense, talked about that. Given that venting of attic or roof spaces is generally still required. The exception provided in the Article 919.11 recognizes that some specialized ceiling roof assemblies, such as those used in some factory-built buildings, have over time demonstrated that their construction is sufficiently tight to prevent excessive moisture accumulation. So I find that interesting that they specifically call out factory-built buildings. That's the part that confuses me. I feel like a better way to say it would be any system that has proven or can be proven to be sufficiently airtight does not need.
Right.
Yeah.
Interesting.
Yeah. And so in reality, what we're seeing in the field is that oftentimes to make building inspectors happy, the except where it can be shown to be unnecessary is a engineer's letter saying that we've looked at this system, we've analyzed it, it doesn't need to be vented.
Right.
There's different approaches to that, one of which is hydrothermal modeling, others just experience or research in the field. So yeah, I found that really interesting that they specifically called out factory-built buildings, but I think it should be a lot more general than that. And then venting requirements. This is the part that most people are familiar with. It says, except as provided in the next sentence, unobstructed vent area should not be less than 1/300 of the insulated ceiling area. So that's our typical vented roof.
Yes.
But where slope is less than 1 in 6, or in roofs that are constructed with roof joists, which I find that a little strange, the obstructed vent area shall not be less than 1/150 of the insulated ceiling area. So if we have a flat roof or a low slope roof, or we have a roof that has very limited, I guess a vaulted ceiling, like where it has very limited air movement above, then we have to use twice as much. So these are obviously very kind of general requirements. And again, like these numbers tend to work well for us for the most part, but just because you meet the code doesn't mean you're necessarily not going to have any problems. And that really comes down to how airtight is your ceiling plane. If you have excessive air leakage, either of these could be not enough. If you have really good air tightness of your ceiling plane, we could get away with much less than this. But if you don't understand exactly how airtight your ceiling plane is, then this is probably relatively good approach for those. Although, like I said before, I don't recommend the low slope roofs to be ventilated because of the reasons we talked about. So yeah, now I've got a couple of forensic case studies. Well, one specifically here that is related to a ventilated roof that had problems. So this was residential. These are the kind of buildings I'm seeing a lot in Toronto. This one, the roof, as you can see, there's no roof overhangs at all. So our soffit vents are out of the question here. There's an integrated gutter system behind this little parapet wall. There's a steep pitch at the perimeter and a flat section on the roof. Also to note that there's ductwork in the attic because that became an important factor also. So just to kind of show that in a real simple form, right? We've got our main part of our building with our air barrier. We've got our roof sitting on top. We've got just blown in insulation. We do have some ventilation. I'll show you a little bit later, lower down in the roof. And we actually have quite a bit of ventilation at the top of the flat roof. And this is to represent our ductwork that goes up into the attic. So what were the issues? The issues were that the first issue that came up was they were seeing water marks, water staining on the second floor ceiling after a long cold spell, once it warmed up after a long cold spell. So once they thought that that was potentially an issue. They went up into the attic on a colder day and found excessive amounts of frost buildup on the roof sheathing. And this is actually at one of the vents. So I'll talk a bit more about. This is actually supposed to be an intake vent, but because of the dynamics of this roof, it actually ended up being more of an exhaust vent, even though it was lower down in the ceiling. So the first thing I did was to evaluate the ventilation. So it turns out there was sufficient ventilation high up in the roof to meet code. So there's 4 12-inch round vents. I think actually 1 or 2 of them were the whirlybird vents, and we did suggest they change those to static just to avoid some of the problems we talked about with negative pressurization.
Mm-hmm.
The big problem from a ventilation standpoint, where there were very little low ventilation. These were integrated into the steep part of the slope, very small, 1 inch by 8 inch vents, and there's 6 of them on the whole building.
Wow.
Yeah, and so what you could see, this is what it looked like without the frost, and this is what it kind of looked like on its worst days. Yeah.
Right.
Yeah. So we did the ventilation analysis, and we said, yeah, there's definitely not enough low ventilation. There's also some other problems. We've got the ductwork itself was actually very leaky. It was covered with open cell spray foam. And this is just one example of the gaps in the open cell spray foam we could see. We could feel.
So open cell, so it'd be more of a, let's say, some would call it a open cell, some would call it like a half pound or foam. So it's a air barrier certain, but it's not a vapor barrier, is it? Either. Right.
And it's not an air barrier when there's big holes in it.
Right.
That's probably the biggest issue.
Yeah.
I believe that they were counting on that spray foam as the ceiling for the ductwork.
Oh.
And I did find later in the code that it's very specific that while you're allowed to put spray foam on ductwork, prior to that, you need to air seal it properly.
That's right.
And there's that calls out a few different ways to do that. So one thing I had to teach the builder right away was that we can't count on spray foam at all to seal ductwork, and certainly we can't count on half pound or open cell spray foam to seal anything really. Ductwork. Leaky ductwork, insufficient low ventilation we talked about, and we did also find some pretty significant air leakage at the ceiling plane through pot lights and some other detail areas that were not properly done.
Yeah. Was the primary air barrier in the building an interior polyethylene?
Yes,
approach?
In this case, it was an interior polyethylene. There was lots of pot lights, as was pretty standard. There were boots over the pot lights. They weren't well sealed.
Okay.
And there were a few areas where there was sort of some double walls that didn't really get tied over top of properly. So all 3 of those were contributing to, so we're in this case, we're out of balance. Our balance is gone because we're putting too much warm, moist air into the attic, and we have too little ventilation to avoid accumulation. So what do we recommend? We recommended properly air sealing the ductwork. We recommended properly air sealing the ceiling plane. And they did that. We recommended installing more low vents. They couldn't really add too many more. They did add, I think they doubled the number. They're still not very effective vents the way they're designed and the way they're positioned, but we added quite a bit more. And then as a temporary fix, we added this inline fan and attached it to one of the low ducts. And what we were doing here is we're drawing in cold air. So as opposed to a power vent, which is pushing air out, we're forcing air in because there was so much moisture accumulated in the sheathing and in some of the wood members that we needed to dry it out for a month.
Yeah. And the air seal, when you say air seal, it looks like what you were using to air seal that, because it's a complex geometry. Is that a closed cell spray foam, like just maybe a single lift?
Yeah, there was some closed cell spray foam used at tricky areas to make that seal.
Okay.
And it's not always the best way to approach that. Obviously, if you're doing it from a design standpoint, you wouldn't say make it all mostly poly, and then use some spray foam, because
Right.
the two don't play together that well, but
Yeah.
we made major improvements in the air tightness of the ceiling plane.
Yeah. Good.
And then use this fan temporarily to dry out the attic. So a bit of a summary then, some of the benefits of vented roofs for residential. They can work in any climate. So they work in cold climates and hot climates really well. Generally speaking, they're cheap and easy in that, you know, we can use lots of loose fill insulation if we want. We can get high R values without, you know, too much cost. We're really familiar, the trades are really familiar with the polyethylene air vapor barrier, and it's readily available and cheap to use. So this system can tolerate some air leakage from the building into the attic, right? So it can flush that out if we have enough ventilation. And also, an attic like that is really good at drying out. Once the weather changes from cold to warm, or even just a hot day, even on shoulder seasons, a lot of drying can occur because the attic is vented. So
Okay.
we even if we do get some accumulation of moisture in the attic during the winter, as long as it's not too much, we can dry it out quickly once the weather changes. What can go wrong?
Any thoughts, and you don't have to answer, you don't want any thoughts on the difference between, say, a plywood versus an OSB roof sheathing?
Yeah, I don't think there's I think there is some difference, but not a lot of difference.
Okay.
In terms of ability to withstand moisture. What I think they'll both absorb moisture and become wet really easily. I think the only real difference is plywood will last a bit longer being wet. Instead of seeing your roof sagging after 3 years, it might take 5 years or something.
I see. Okay.
They're both gonna break down, and OSB will break down a little faster, but I don't think it's a major difference between the two.
Good.
Yeah. So what can go wrong? Too much air leakage, right? So pot lights, attic hatches, we see over pressurizing the building. If the building is being pressurized by the mechanical system, that can force more air leakage into the attic. And same with negative pressurization of the attic can be a problem, as we talked about. The other thing, just not enough ventilation. So we don't have enough free area. So if our vents, sometimes we have clients who want these fancy vents that don't look like vents, but they also don't work like vents. So they need to function. We need to have enough free area in the vents to allow that air movement. If for some reason we don't have enough stack effect, so we don't have the height difference from the low to the high vents, that could be a problem. We also see areas of the attic blocked sometimes by framing and creating dead areas where some of the attic is well ventilated, other areas maybe not so much. So we have to watch for those. Sometimes it can be a localized problem. Even if you meet code overall, there might be some localized issues because of blocking and geometry of the roof. And we also have to worry about other moisture sources. HVAC ducts, right, in an attic, in cold climate, very risky. Rain, snow penetration through vents can be a problem. And the other thing we haven't really talked much about is, but if the house is running at a high indoor relative humidity, then that air that does leak through has more moisture to deposit. And you will see problems a lot faster than we would running a normal RH.
I remember John, Straub jokingly saying, someone asked him, well, in Canada, so zones 5, 6, 7A, what about interior RH? And John said, well, just off the cuff, if you're running interior RH in the wintertime of 50 to 60%, all bets are off on your house. And I think it's interesting because we're at this time of this balance, right? We can't have too much, and yet we can't have too little either. So it's, again, that old adage of that 25 to 30, I think, the Canadian Building Code assumes about a 30 to 35% RH in the winter time.
That's correct. Yeah, and it's really difficult to put that into code because you could have, a 5,000 square foot house with 2 people living in it. And how do you manage? You probably need to add some moisture to that building. Right. And then the work I do in the far north in Nunavut, it could be 12 people living in a 1,200 square foot house.
Right.
And you can imagine how much moisture they're generating and how do you keep it low enough to avoid condensation, not only on the windows, but inside the walls and inside the roof.
Right.
Right?
Okay.
So yeah, it's difficult to put that into code because we use our buildings in so different, so many different ways, and they see so many different stresses. So it's really just something. It's good to understand, though, for sure, and try and account for that. So unvented roofs. So sometimes, as we know, we don't want to vent our roofs, and we'll talk about what those circumstances are. We're going to talk about why unvented roofs usually work, and sometimes they don't. So when should we consider changing from our normal vented roof to an unvented roof? I think when roof lines get really complex, there's a lot of blocking, a lot of framing, dead ends. We've got, dormers and roof sections that become walls. When things get complicated, it becomes difficult to properly ventilate. And so we should start to think about whether an unvented roof's better. Certainly vaulted ceilings. If we're going to have vaulted ceilings and we don't want a large attic above them, we probably are going to want to consider unvented for that. Low slope roofs, flat roofs. We talked about why that is, because they don't have the ability to constantly ventilate themselves.
And Trevor, I'm going to ask you to remind us again, what would you consider to be low slope?
Less than 312.
Okay, less than 312. That's a good point. Just a good rule of thumb.
It's a good rule, and that's where that's the general rule for using different roofing materials, right?
Yeah. Is it the building code assumes that a wall becomes a roof at what? Is it a 2412 or?
Yeah, we had this conversation. Yeah, I forget how it defines it for sure.
Okay, that's okay. Don't worry about it.
But I think the thing to think about is if it's connected into the roof, it's connected into the attic, then we should try and treat it like a roof as opposed to a wall. Because if there is communication of air between the two, yeah. So yeah, it gets blurry for sure. Yeah, so let's go back to that commercial unvented roof, the super simple one that just works. Okay, why does it work? Well, first of all, we've got multiple layers in this roof acting as an air barrier, right? So we've got our fluted steel deck, or even a wood deck with trusses, whatever you've got here, and you've got some type of sheathing over top of that, and a specific air barrier, and maybe an air vapor barrier right at this level. Then we've got layers, probably multiple layers of rigid insulation, staggered joints potentially, and then a whole other layer of probably a fiberboard or something to hold our roof membrane, and then the roof membrane itself, which is continuous. So all of these layers are air barriers to themselves, really, and when you start to stack them all up, there's very limited risk of air moving through this assembly because of all those air barriers. The other great thing is now we've got, in this case, our insulation is exterior to our structure. So that means our structure stays on the warm side. If warm, moist air from inside gets up into here, there's no cold surfaces for it to condense on. So we don't have to worry about condensation down at this level. And really all we need to worry about in a assembly like this is penetrations and transitions. How do we transition from roof to wall? How do we deal with a chimney poking through, right? I think I have some examples of that. So in this case, you could see and I do see problems on flat roofs, and it's almost always these two areas where things penetrate through. The air barrier, which is down here at the bottom, doesn't get properly sealed. It's not continuous at these penetrations sometimes, and we'll get air leakage and moisture issues around it. And we'll see condensation and wet sheathing up here at the top of the penetration. The other thing we see are parapets. So if this air barrier comes to here and just kind of stops because this parapet was put on before, what's to stop warm, moist air that's in the building from going up into this parapet and finding cold surfaces to condense on.
Yeah.
So
we've actually seen, and you probably have too, spalling or fluorescence or subfluorescence, whatever is sometimes occurring in parapets, and it's from the air leakage that's working its way up in there and then leaving the water. That's interesting.
Yeah, I was at a swimming pool where we went bright and early in the morning. It was like minus 15, I think, out, and there was steam coming from under the parapet cap. Right. So what we need to make sure in this case is that the air barrier is put on continuously under the parapet and ties in to the wall system air barrier. And so we see this now a lot more, is that there's a strip of air barrier that's installed before this parapet's built. And we just have to make sure we tie in properly on both sides of that after. It's really a construction sequence thing. And we need to make sure that that strip that we put in doesn't get damaged during construction and that it gets properly tied in. But those are the two areas really that we need to, really are the only two we need to be concerned about in this commercial style flat roof. But what we realize in residentially is that this is a pretty expensive way to build a roof compared to how we do residentially. So it's not a common approach. So what are the approaches we're seeing in the field residentially when we get to unvented roofs? The first one, and notice the big red not recommended. I used to have it down here small, and someone said that looks terrible. Like that's, I'm like, oh no, it's not recommended. Sorry, but it happens. Yeah. And that's just basically sticking batt and a polyethylene air vapor barrier into a roof. So this could be sloped or it could be flat. In all these examples I'm going to show you. Yeah. Same theories are important. So this bad insulation has no ability to slow down air. And so we're completely counting on our polyethylene air vapor barrier. And as we know, in most cases, that is not a really good, not a very good air vapor barrier, which it would have to be. It would have to be almost perfect for this system to not fail. Because any moisture that gets past our air vapor barrier here is going to start going up this slope, meets the cold sheathing, condenses. It's going to build up tons of moisture very quickly. Yeah, and that's why this is like something we see still sometimes, but it's definitely the not recommended approach. So what are some of the recommended ones we see? Obviously, this is basically a residential version of that commercial roof. All the insulation's on the exterior of the sheathing. The air barrier is exterior to the sheathing. And so we also don't see this very often because it is a rather expensive way to build. But this is the sort of ultimate way to do an unvented roof. It's easy to make the air barrier continuous. The insulation's all exterior to the structure, so the structure stays warm, it stays dry. But even in this, we have to worry about penetrations and transitions, because that is, always going to be an issue we need to deal with.
I think I remember, was it Steebrook Joe talking about he did this on his barn, and he made the same comment that Gord Cook made when he did this on his cottage, is that just make sure you put a slipstream material in between the insulation layers, because as it gets hot outside or cools, they move. Yes. And I remember Gord saying they would be inside the house and it's dead quiet and they'd hear this clicking sound.
Oh yeah, ratcheting.
And then the other thing too is the importance of offsetting the
butt joints.
Yeah. But anyways,
Joe, if anyone hasn't seen it yet, there's a great article from probably 10 years ago now by Joe Steebrook on the lessons learned from his barn. Yeah. And in that he put one very thick layer of foam insulation. I think it was EPS. And he has pictures where you can see frost where all the joints are because of the expansion and contraction. And so one of the lessons learned was multiple layers, stagger the joints. But overall, a super safe way to create an unvented roof, whether it's sloped like this or flat, same thing. But what are we seeing in reality? So I'm not seeing a lot of this in the field. I've got builders who do a lot of unvented roofs. they haven't gotten to the point where they're comfortable with the price of this and the constructability of this. So I'm seeing some other things that are similar, and they seem to work. They seem to be working well. So one example is what we call a split insulated system. In the split insulated system, we have a certain amount of foam board insulation on the exterior of the building, or exterior of the sheething. And then we have a certain amount of batt insulation on the interior of the sheathing, so between the joists, typically. So what this does is it warms up the sheathing to a certain point, depending on what that ratio is. And we have two options of where to put the air barrier here. We could put an air barrier right under, like on top of the sheathing and under the rigid foam. But we can only do that if we have enough rigid insulation so that our dew point temperature doesn't get reached in here. And it's all about the ratio of how much insulation is outside versus inside. In our climate, like in Southern Ontario, 50-50, 50% R value outside and inside would be very safe. You could probably get away with maybe 1/3, 2/3, but we generally I would only do that after a pretty intense analysis, hydrothermal analysis. If you're going to try it and if you use 50-50 in Southern Ontario, you're going to be fine. Now, if you're going to try and do this in Winnipeg, it might be a little different. If we're going to go up into Northwest Territories, Iqaluit, these ratios are you're going to need much more exterior insulation.
So for us in Canada, what you're saying is, we do have the inboard outboard ratios for the walls,
yes,
which have a certain percentage. But let's be really clear, that is for a wall assembly. Yes. To your point, Trevor, when you take that wall and you flip it like this, now you've got the added concern of more pressures, more, so you do have to be a bit more than just using those inboard outboard ratios. Now, is it a simple two-dimensional, analysis, or would you recommend something that, for instance, like a WUFI analysis that could do that?
Well, you could do a simple dew point calculation.
Okay.
But when you do that, you're being like extra cautious. Because in reality, it's okay if you get a little bit of condensation on the underside of here at the worst times of year, as long as it doesn't accumulate over time. And a WUFI will catch that. It'll allow a certain amount. You can monitor the moisture content of this layer, as opposed to saying, is there condensation or not? It'll say, is that condensation accumulating to the point where it's getting dangerous for the wood, right? So even OSB, plywood, it can absorb a certain amount of moisture safely and just release it later. But if it has too much moisture for too long, that's when we see structural problems, rot and mold. Yeah, and you made a really good point about the difference between a wall and a roof, in that the roof always has that stack effect pressure trying to press air out, so the risk of air leakage is higher. And the other thing is the fact that the roof is more exposed to the night sky in the winter. We've measured this. It's been well documented that a roof in the winter will get a lot colder, the surface temperature of a roof, than a wall, because of the exposure to the night sky.
So deep sky radiation, especially on a clear night, it'll cool off. It loses its energy. Isn't that cool? Okay, well, that's interesting.
So a roof is always a bit more extreme than a wall for those two reasons, and we need to account for that.
Okay.
Yeah. So I'm seeing a little bit of this split insulated type system in the field. And like I said, as long as you get your ratios right, and if you do, you can use an air barrier at this level, which can be very effective, make for a very effective air barrier on top of it. And it's just a matter of figuring out the best way to tie it into the air barrier of the wall system. Because at some point we have to pass down through and tie into the wall, and figuring out how to do that. The other thing I'm seeing probably a lot more of is just a pure interior installed spray foam roof system. I'm seeing only 2-pound closed cell spray foam typically for this, and I would only recommend that in our climate, at least. In this case, so what we're doing here is we're using our spray foam not only as the insulation, but we're using it as the air barrier. And so it's really critical, though, that when we're installing that spray foam, that it's installed in an airtight manner. So we have to worry about air. Some areas aren't covered by the spray foam. So if you have a doubled up joist and you spray foam to each side of it, you still have that crack at that, where those two pieces of wood meet. And we need to seal that separately because that's got to be part of our air barrier system. So the insulation in this case is all interior to the structure, which means if air is allowed to get around it at cracks or at areas that are missed and can reach this sheathing, that sheathing is going to be cold and we're going to get a lot of condensation there.
Mm-hmm.
So that is the risk. And we always, like everything, we have to beware of penetrations, things that pump pass through, and transitions. So how do we make the air barrier of the ceiling or roof meet with the air barrier of the wall system properly?
Yeah.
So those are the details that really need to be worked out.
And I know there's some sorry, Trevor, there's some concern too. And I know there's some comments there. We have seen the spray foam crack. So for instance, it's not supposed to do that. But again, I think that comes down to the conditions, right? Is that fair to say?
Yeah, the installation conditions are key for sure.
Mm-hmm.
I will talk a bit more about that because I am a lot of the work I do is like third-party inspection of spray foam roofs for these reasons. And so I'm extra cautious about that. The other extra thing though that we have to worry about a little bit with a purely spray foam roof are fire considerations. So if this was a vaulted ceiling and we had drywall directly below it, that's fine. But if this is an open attic, but we want to spray foam to the underside of the roof and there's an access to that attic, we start to get into some fire code. And there needs to be, I believe they call it there's a couple different terms they use. We do use intumescent paint.
Okay.
And it's a ignition barrier.
Ignition barrier. So like
it's not fireproofing, but it's ignition.
That's right. Yeah, I think it's I think the term is, and maybe someone can correct me on here, but I think it's a Class B thermal barrier. So, it had, like you said, drywall or steel. I think there's some wood, plywood, or dimensional that works, but also like a rock wool or a thermofiber at a certain thickness can act as a Class B.
Yeah, I know that there's two different levels. One, if it's accessible space, but it's not living space, then there's a lesser fire requirement than if it's living space.
That's good to know. Okay.
Yeah. And that's why the intumescent paint will work. I think if you have an accessible space that's not living space, intumescent paint will qualify. But if it's living space, then you need the full drywall, wood paneling, or whatever other fire.
Yeah. So in those rare occasions where the foam is going to be exposed and you can access the space, then you're going to need something to cover that. Yeah. Absolutely.
And in my experience, that's not rare because there is in the custom houses I'm working on, there's a lot of ductwork and stuff up and mechanical stuff up in that attic because they've created that space for it. And so it's definitely accessible.
That's right. Yeah, absolutely. Okay.
Mm-hmm. And then so there's sort of another version of spray foam unvented roof design we call flash and bat, which is a combination of spray foam and bat insulation or blown-in insulation. And so what we see here is a certain amount of spray foam installed directly to the underside of the roof deck, and then filling in below that to get more R value with either bats, which you could see might be difficult to do depending on how smooth this is or if there's anything to hold it. What I'm seeing more of are blown-in bats with mesh or netting.
Oh yeah, like a blow,
bibs, yeah. And so the same cautions apply here because in this case, the spray foam is still our air barrier and it needs to be continuous, and we need to seal wood to wood joints that don't get covered by foam, and we need to make sure that the installer didn't miss a spot. Even a little gap could create problems. Mm-hmm. And we have the additional issue here is similar to our split insulated where we have exterior, interior, we have to make sure that the ratio of spray foam R value to bat R value is acceptable. And again, that 50-50 is a safe number to use, because if we use too little spray foam and or too much blown in, we're going to have condensation forming on the underside of the spray foam potentially if it's too cold.
So another dew point. Yeah.
Yeah, we could still have a dew point problem if we don't have enough spray foam here. So again, that 50-50 rule will be pretty safe in Southern Ontario. It may need to be more in colder areas than that. And just like anything else, I'll keep saying it, beware of penetrations and transitions. That's where we see most of the problems, where things are poking through, especially, well, I think I have some examples coming up, but yeah.
So just like with a vented assembly, with poly and that you're saying the same for here, is it's the, compromising the air barrier. It's the penetrations that cause the issue.
Yes.
It's the pre-wire folks that come in afterwards to do the speakers or the fancy pot lights or the, you name it. So, yeah.
Or we forgot to put in a certain vent until near the end and the spray foam's already there. Someone cuts through it. Nobody really checks that you didn't cut the hole twice as big as it needed to be through the spray foam. That's the sort of quality assurance, quality control side that's really important, for a lot of things, but especially for spray foam, I think. And so, just some examples, because I do so much of this inspection work. When I'm doing, I kind of have different levels of inspection, but the highest level of inspection I do is to negatively pressurize the building during the inspection and use thermal imaging to look for leaks, and it works out well for photos for sure. But rim joist areas, this is really classic. A lot of times the spray foam installer is shooting at an upward angle, and in the rim joists, and there's a little bit of shadowing in there. If he doesn't shoot down onto the top plate, there's often, as you can see here, these little gaps, and you can see what that looks like as soon as the building's under a bit of negative pressure. We can get quite a bit of air leakage coming through those areas.
So they need to connect that spray foam air barrier to the top plate, or the air barrier in the wall is what you're saying. Okay.
Exactly. Okay. And it's especially important where each joist rests on top of that top plate.
Okay.
It's all about spraying angles and
Good. We just got the 10-minute mark for you, Trevor. So
that's
feel
perfect.
free. No, we've got some good questions. So keep rolling.
That's going to be perfect. We're almost there. Yeah, so just some other examples of air leakage spots. When we try and transition from spray foam to poly, that can be a tricky proposition. So we got to be careful there. Where we have these like bigger penetrations, especially wiring is tough because it moves. It's not like a solid surface. And so as an example of a really bad thing, air leak I found pretty easily. You didn't really need IR to see this one, but we used it. And the other one that's actually really tricky is fireplace vents, because we can't spray foam up to them like we can with a bathroom vent. Right. And so there's special detailing we need to do to make sure that we have something that carries the air barrier from the outside of the fireplace vent outward and ties into the spray foam in a safe, fire-safe manner. So there's sheet metal and fireproof caulkings and stuff that you need to utilize to do that. Just a special example too, in terms of unvented roofs, would be SIPS panels. Just some cautionary tales about that. In a cold climate, we really have to be concerned about air leakage at the joints of the panels, and especially where the panels sit on, for a roof especially, where they sit on ridge beams or purlins, that we have some type of air sealing that goes on before the panel that we can tie into. Because once the panel is sitting on here, there's no way to then air seal the joint all the way up in a 3D manner. And so there's been some pretty well documented issues of what we call ridge rot in SIPS panels in cold climates, because some of these details were missed. Warm, moist air can get into the joints and travel up to the peak where they can deposit, water due to condensation. So just sort of there's no, panacea. There's no, silver bullet here. Whatever system we use, we have to make sure that our quality control is really good, that the air tightness of the system is really good, because the only way an unvented roof is going to work is if the air tightness of the ceiling plane is very good. Real quick, a little case study related to a unvented spray foam roof. This was actually the design, which it wasn't built this way, but the design was supposed to be 2-pound closed cell foam to the underside of this deck and down each of these parapet walls. But what in reality, I guess when the contractor got there, they thought it'd be a good idea to switch to open cell foam. So they said, okay, we're going to use open cell foam, 1/2-pound foam instead. And they knew that because they're using open cell foam, they had to use a vapor barrier. So they did put a poly vapor barrier in. But what they didn't do is treat it like an air barrier. They just kind of left it flat here at the concrete block walls. And so what they saw over time was a lot of warm, moist air was getting up into here. When we opened up, you'll see a bit of the demo pictures. There were actually a lot of voids and pathways even through the spray foam. So it wasn't well installed. And a lot of warm, moist air and moisture accumulation was happening in this little space where they created the sloped roof that they could walk on up here. And so what does that look like in reality? So the sheathing near the parapets, the sheathing was completely rotted out, and some of the eye joists were starting to rot out.
Oh boy, now we're into structural.
It started to become structural. Here is an example of the poly from the ceiling that was just kind of dangling. I could just pull it up. It wasn't sealed in any way to that block wall. It was just loose. And so how did we fix it? They definitely wanted to fix it from the exterior. And so what we did was to basically create a split insulated system by adding rigid insulation to the outside, adding a new air barrier, okay, so that no air could get past this green plane, adding a significant amount of exterior insulation above that and over the parapets, and then a whole new roof deck on top of there. So in this case, that warm, moist air is still going up in here, but it's warm enough in here to prevent condensation.
Right. Interesting.
And that was the way they decided to do it. It was a pretty expensive way. They lost some height and they had to move a bunch of railings and stuff, but they wanted to do this as opposed to going into the units and disrupting the tenants. So real quick recap, what are the benefits of unvented roofs? Great for low slope and complex roof systems where venting is just difficult or it's not going to be effective. It's probably going to be easier in an unvented roof to create good air tightness because we can oftentimes use continuous air barrier on the exterior that's not penetrated through by mechanicals nearly as much. So we're not relying upon questionable amounts of venting for performance. We just know there is no venting and we're going to make sure everything's airtight and well insulated. And we know that there's a proven track record of these commercially. We just want to try and make our assemblies as close to that commercial, assembly that we know works as possible. What can go wrong? Spray foam is an air barrier. We talked about must be installed with a lot of care, and I always recommend third-party inspection for the continuity of the spray foam as an air barrier. The other thing that can go wrong is we have to make sure we use enough exterior insulation to avoid dew point problems in that split insulated or that flash and bat system. And like anything, detailing the penetrations is also really important.
Very good, Trevor. That's awesome. That was excellent. And of course, we could take up a whole nother session, and honestly, with the questions, we may have to do a version 2 of this, just so you know. So get ready for that one. I did want to note over in the chat, folks, Trevor, you're probably aware of this, you might have worked on it. There's a really nice guide BC Housing has that has a lot of good detailing for low slope, effective 30 roofs and so on. And I see some of your detailing and building sciences in that. Again, it's free, so hop on there, folks. All right, let's jump the questions. We've got about 12 questions. We've got about 15 minutes. So some of these are statements, some of them are questions. So we're going to start out. the Daryl Paul just asked the question, unvented, are they hot or cold roof assemblies just in general? What would you call them? And I think you were
right. The term hot roof is basically an unvented roof.
unvented roof.
Yeah,
Okay.
they're synonymous with each other.
Okay.
Yeah. Whereas a cold roof would be a vented.
Yeah. Okay. George Enrique. George, a great guy. Great architect and builder. George is wondering. He says, hey, are there alternative ways to do venting without the soffit overhang? And I'm going to assume that we're still talking about a decently sloped roof.
Yes, there's certainly ways. There are products out there like Cobra Vent and different things that allow for adding ventilation on a slope. But there's definitely risks to that in terms of moisture intrusion and the fact that it will take a lot because of the net free area of those tend to be pretty small. You would need a lot to get an appropriate amount of ventilation, but it is possible. And the steeper the slope, the better to use a product like that. But it is possible with, I can't remember all the trade names, but Cobra Vent was the one that jumped out at me. Good.
Joe Somfe says, can you just add a comment on roofing color?
Sure. Yeah. So one thing I would add is that there are some specific issues came up when some unvented flat roofs were switched from a black roofing membrane to a white roofing membrane. And some of the investigations showed that the black roofing membrane would get warm enough and heat up the system enough when it was warm out to dry the system out. Whereas when it was switched to white, it didn't have the same drying capacity. Yeah. And so it must have been right on the balance point. And this just hit the balance enough that moisture would accumulate in the roof because it doesn't have as much drying capacity due to the lower temperatures.
But Trevor, we got our lead points for it. We got that low LB, white roof. I mean, come on.
But that's a great example of how close to the balance point some roof systems are. Like if you change one thing a little bit, it might tip it the other way.
Yeah, good. Tammy asked a question: What would in your thought the minimum difference for the optimal ventilation between the low and the high vent? You talked a little bit about needing a certain height distance or so on.
Yeah, you want to maximize that distance for sure. I don't know if there's basically the greater the difference, the more stack effect you're going to get. So obviously you're limited by the design of your roof, but to keep the lows as low as possible and the highs as high as possible is the way to go. And once you start to get into those, less than 3 and 12 slope roofs, you're probably not going to have enough height difference to get good ventilation.
That's good. That's a good question. That's a helpful answer. Daryl Paul, just a comment from Daryl. Daryl, good to have you. Daryl's done a lot of great work for the industry. Just recommend, he says, I highly recommend a pre-drywall air tightness for, let's say, some of the spray foam. They see lots of failures in that case.
Yep.
Sounds like you would.
Yeah, I don't technically do air tightness tests, but what I do is pull a negative pressure and go room to room, and either if it's cold outside, I'll use my IR camera to look for leaks, specific leaks. I'll mark them. I've given reports to clients with 35 corrections to be made, each one numbered with a marker on the spray foam to say he's got to come back and seal that. You can seal this one with some canned spray foam, but this one over here, you need a whole nother pass of low cell. So we get in these long reports with maps of where all the issues are to make sure we can avoid that. But air tighten, using air pressurization to help you is a great idea.
Yeah. He just Daryl, to that point, I know our team too has worked on some projects with Trevor and others where we actually do when we get attic rain or frost, what we'll do is we'll do a zonal test. So we'll depressurize the house and put a manometer tube in the attic, the house, and the outdoor. And what'll happen is if there's substantial air leakage, what'll happen is when you depressurize the home, you actually will depressurize the attic as well. And we've seen that scenario in some of these tall 3-story townhomes, right? They got nice eaves details, makes them really tight, and they've got attic rain. So we go in, we put the blower door up, we depressurize it, only to find out that when we depressurize the townhome, we also depressurize the attic by 5 to 10 pascals. So
yeah, that's a great diagnostic approach too. Yep.
Daryl just made the point too that, he said foam doesn't have the same storage capacity compared to the fluffy stuff. Now that could take us down a rabbit trail. I don't know if you want to talk about that, but
I'd say neither one of them have very good storage capacity. Yeah,
that's good. Just keep make them both airtight, and
keep them dry. Keep them both dry.
Jim said, he said, I had the understanding that in Southern Ontario, so I'm going to assume that's like zone 5, climate zone 5, the ratio of insulation on either side of the air barrier for a wall was 1/3 inside, 2/3 outside. For the roof, you mentioned 50-50 is safer, but is that not riskier ratio for a more challenging condition?
Yeah, so the ratio you're talking about that's what I would use in the subarctic. In Southern Ontario, I know even 1/3 outside, 2/3 inside is very safe. And you probably get away with more like 20% outside, 80%.
You do. The inboard outboard ratios that speak to low permeance exterior sheathing, say, I think zone 5 is a 20%.
That's pretty safe in our environment. I've tested walls with 1/3, 2/3, and even at really high interior humidities, we couldn't create condensation with air leakage.
Okay.
But in reality, I think that the 20% is a pretty good number for Southern Ontario. Yeah,
good. But again, I want to remind folks, to your point earlier, Trevor, a wall is one thing, a roof is another.
Yeah, so, everything's a little more extreme.
Yeah. Jim said, just a question about a deep parallel truss. Is there a problem if there's an airspace between the flash and the bat?
We definitely wouldn't recommend a gap. There could be. It probably wouldn't be a problem as long as you have your ratios still correct. That if there was an air gap there, it probably wouldn't be a big deal. But it is a good practice to keep the materials pressed together to avoid a little more of the. It's not as big a deal on a roof. It's actually worse on a wall, because what we're trying to avoid by keeping our materials together are the convection loops, which is a bigger deal on a vertical surface than it is on a horizontal surface.
Interesting.
But it's still a good idea to avoid those air gaps if possible, but not as big a deal on a roof.
And this sort of goes to the next question from Brett. He just said his question was around, is it okay to have voids in the roof assembly? Will it set up convection current? So I think you answered that a little bit, but I want to go a little deeper on, Brett. What if there is a gap between the drywall and the face of, let's say, the closed cell foam that you're using? Is that okay?
Yeah, that's okay, because you don't have that temperature difference. The air above the drywall should be very close to the temperature of the air inside the building. So all of your temperature drop is happening across the spray foam still. To get convection, you need like that temperature difference to sort of drive those loops. That's why you wouldn't want a gap between pieces of insulation. But if it's a gap interior to an insulation is okay.
Okay. Yeah. And that's that little nuance, right? A lot of building science training is the insulation has to be in contact with all 6 sides of the assemblies. Okay. Well, anyways.
Yeah.
Jim practice. Says, just a question, and I know you probably get this one. For a flash and bat, if you're using like, let's say a closed cell, assuming I'm assuming it's closed cell and bat, should you avoid installing a vapor retarding barrier on the underside of the bat? So I think he's alluding to a double vapor barrier type of barrier.
Right. I would suggest that you would always use enough spray foam in your flash, so at least 50% of the R value, that you wouldn't need to use any air control or vapor control in the interior. So I would avoid that. It's possible that you could create a moisture trap. It's not probably all that likely, but I would still always suggest using at least 50% of your R value in the spray foam, and then avoid poly altogether.
Okay. And that's a question we get a lot too, whether it's roofs or walls. You know, if
Mhm.
I'm using closed cell spray foam or rigid insulation that's, you know, low perm, but it's an air barrier and I have it in the wall or the roof, should I still add poly? And, you know, it's all that concern there. And to your point, good recommendation that you wouldn't have to if the air tightness
Right.
is there and the dew point control and the insulation value is there. But the code isn't clear, is it, on that one?
True. No, it's not clear.
And
It's kind
like
of
in
like
the
our where it is deemed necessary or unless
Yeah,
deemed
yeah.
necessary.
It's interesting, and not to say that things are better south of the border, which I don't think they are, but you know, a good Canadian that we know, Joe Steebrook, helped them figure out in the IRC that sort of ratio, right? If you've
Yes.
got R10 on the outside of a 2x6 wall, you can use a type 3 vapor retarder. We just haven't got around in Canada to figuring out how to get rid of calling things vapor barriers.
Right.
So,
Right. Yeah, we do often get into writing letters for code officials for that very reason, just because, just
interesting.
clarify it. This is going to work. We've analyzed it. Yeah.
Yeah, good. So we've got about 4 minutes left. Dan says, just maybe more of a comment, a question. He said, I've seen a demonstration of aero barrier sealing product that's used for new construction for sealing ductwork too. It's
Yep.
quite impressive. So
Mhm.
that's great.
Nice plug.
There you go. So there's your point, Trevor, maybe on a retrofit, right? You got that foam up there. Maybe
Yep.
they can go in and do aero seal to seal the ductwork, like you said, needs
Yep.
to happen. And then they continue with the
Yep.
around the outside. Russell Ibison, Russell, good to have you. There's another building science guy, honestly. But anyways, so how would you approach bringing a skylight shaft through a vented attic, considering the concern about adequate ventilation below the shaft in the attic, which can contribute to ice damming? Ooh.
Yeah, that's always a tough one. And chimneys too, they can block anything that can block your ventilation flow. Gets really difficult. What I have seen, it seems to work okay or better than nothing, is to cross strap so that if you've got your joist running down, to cross strap the other way. So there's at least always that 1.5 inch gap for lateral movement. So if air is trying to travel up and it meets a dead end, it can at least go up and over and around, whether it's a skylight shaft or a chimney. Whereas if something completely blocks that pathway, you're going to have moisture accumulation there.
Yeah.
Of course, that would be for like a vaulted ceiling kind of situation. If it's an open attic, then air can move around it. It's fine.
Okay. Okay.
Yeah.
Couple statements, Peter Gogich, I think I pronounced your name right, Peter. Anyways, just reminding us that, you know, you folks can read his QA comment, you know, regarding spray foam. It's critical, he says, for the application to test and verify the applicators did a good job. He said, you know,
I agree.
he said, you know, these things are rampant in Alberta where they've got really severe, and it's not just severe temperatures, but severe temperature swings, right? With Chinooks and everything else happening. So great comment, Peter. Stefan Chandler said sloped vented attics allow, you know, inexpensive sustainable blown installations, but flat on vented attics allow you to maximize. Should we all be going to traditional commercial roofs for sustainable buildings as much as possible? Question mark.
I would say if you are trying to build your building to the highest point that's allowed in the zone, and you want your living space to be as high up as possible, then that's probably the only way to go. If you don't have height restrictions, you can still do a really good ventilated roof. It's just that you've got that, you know, part of your building that is using up, which may be valuable vertical space, is a vented attic.
Okay.
So I don't see it from a sustainability standpoint being better than the other.
Okay. Interesting. Couple more questions. We'll sort of fire around here. Trevor, are you okay to stay on for another 3 minutes? Can we go overtime?
No problem.
Beauty. Okay,
OT.
Stacy, if that's okay with you, we're going to go into overtime. Promise you no more than 5 minutes, but we have good questions. Scott Phillips from Building Knowledge Canada, I think, anyway, says, if a builder is going to do their first attempt at a low slope roof, so let's say it's a 212 or less with no room for venting, what would you recommend they pay the most attention to?
Well, first thing I would recommend is they put all the insulation on the exterior.
Okay.
And if they can do that, the chances of success are very high. If they end up doing something else, like a split insulated, or if it's split insulated, then you really need to worry about ratios. And if it's a flash and batt or a pure spray foam, then it's all about continuity and air tightness.
Air tightness. Okay, good. That's a good question. Robert Cohen, really good builder, just says, you know, do you have any recommended details products for the assembly of a flat roof? Trevor, I know you've got a bunch in here that we're going to share with Robert team, but real quick, is there one assembly that you would say, if you're going to do a flat roof, this is my, you know, this is what you do for your mother-in-law? How about that?
Yeah. Assuming you like her, yes. Yeah, the full exterior insulated roof system is the safest. It's the easiest to do well. It's probably the most expensive from a material standpoint, from a labor standpoint, but the details are easy because of the fact that your air barrier can be continuous on the outside of the enclosure. Just makes it easy.
Nice. I don't know if I'll pronounce your name, Fauzi. I think I have that right, but you just asked, what about smart vapor barriers when used along with the insulation? Let's assume it's a rigid or a vapor barrier or a spray foam closed cell air barrier system.
Right. So if you do need vapor control, other than the spray foam, or if you do need interior vapor control, then a smart vapor barrier allows a little bit of drying capacity to the interior, which just gives you a little more room for error, I guess.
Okay.
You think about that balance, that you can tolerate a bit more moisture if your assembly can also dry to the inside if it needs to, as opposed to a polyethylene sheet, which completely shuts off drying to the interior. So you buy yourself a little bit more wiggle room, more safety room.
Yeah.
For handling moisture.
You know, it's interesting, Trevor. We've seen the smart vapor retarder, or what's called in our building code now a variable perm vapor barrier. So that's the term that's used in the Canadian code. And Straub helped us with a little bit of that when you do have things like closed cell foam or rigid foam as the insulation, and, you know, the building inspector, the architect, the builder can't decide whether they still need poly for vapor or not. We oftentimes will say, well, just put in a smart vapor barrier, because then we're all going to be happy. It fits in the code. Now it's going to cost a little bit more, but it seems to work.
Yep. Yeah. The other option would just be like a vapor barrier primer or paint. It's not smart. It's not smart per se, but it allows a lot more vapor movement than poly, obviously, and does give you some drying potential inside if you're worried about that, but don't need 100% vapor block on the inside.
Right. And like they say, what is it? Poly is 30 times more impermeable than it needs to be to be a simple vapor barrier by definition of our code.
Right.
So George, I don't know what your question is there, 712. I'm going to skip that unless you want to put it back in to clarify. Matthias says, regarding split insulation ratios, are you talking about nominal or effective R values when you say a 50-50?
We're talking about nominal because the worst case scenario is through the insulation. In our case, even if you go through the stud, then that makes your ratio even better. But what we're thinking about is through the middle of between two studs. So that would be more nominal.
Okay, good. And Dave McCauley, last question I think we'll be able to take for today. Dave, excellent architect. No, Dave, very well. Good to have you on, Dave. He says, have you found some issues with cracks? And I'm assuming this is talking about spray foam. Oh, yeah, it is. Between rafters because of shrinkage and movement.
Yeah. So I definitely have seen that. I've seen cracks in the middle between rafters of just the spray foam cracking. And almost always, there's only a couple issues that can really, it's either the mix of the chemicals. That's probably less likely. The biggest thing is not properly preparing the surface. The surfaces are wet. So if the surfaces are damp, it's going to mess with the curing. And the other, and when you put the two together, it's really bad, is too much foam too fast. So closed cell spray foam should be installed in 2-inch lifts with curing time in between. If they tried to put 4 inches, or I've even seen them trying to do 6 inches at once, the shrinkage that occur, the forces that occur shrinkage wise, and the curing process is all messed up. And you can get some pretty dramatic failures that way. So yeah, if the chemical mix is good and the temperature and humidity in the building are good, the next big thing is how are the surfaces? Are they properly dried and free of debris? And don't put too much too fast. And there's the manufacturers have very specific instructions on that. And if they follow the instructions, they'll be fine, but they often try and put in twice as much at a time to get out quick.
Yeah.
Friday afternoon kind of a thing.
Trevor, awesome presentation. And all of those of you that had questions and attended, your comments, really good questions today. It's going to make for a great recording, and we are going to have Trevor back. I don't think we've decided on all the topics yet, Trevor, but we're going to have you back on this. So thank you so much for this. I'm just going to just close us out today. There are a couple things that we do want you folks to know. So we have, if you're interested in, the building science sessions like today, recordings, they're on our website. Come to our website. You can listen to them. You can show them to your team. You can show them to them at lunch. And then there's articles as well that we have, as well that we actually have a building knowledge. It's a digest. It's a building science digest, and it's for part 9. It's for builders. And we do this 4 times a year. There's some great articles, some details, lots of industry updates. Sign up. It's a pretty cool little snazzy digest, building science digest. We do have an Enbridge session coming up on some application systems that are province wide. So that's really particular to the gas applications. And then we have our next building science session is going to be air barriers and vapor barriers. We're going to crash into the topic again about the difference between the two, why they cause us to lose sleep. Do we need to start talking about them separately? Which ones do we really need? Which ones don't we need? And it'll probably be more of a debate than it will be a discussion. So thank you folks for that. Thanks for attending. And Trevor, I got to tell you again, that was phenomenal.
Thanks,
nice
Andy.
work.
And thanks everyone who came out today.
Yeah. And look in the chat, Trevor's email address, his website's in there, Bawating Building Science. Trevor's been a great source for our team, for our builders and clients and many others. Get a hold of him if you have questions. And everybody else, have a good afternoon. And thanks for joining us.
Take care.
Take care.